Well, hi guys. This is 4F, exercise 4F, factorising complex polynomials and solution of polynomial equations, part 2 of 2, a little video mini-series. We're going to review again the fundamental theorem of algebra, which is super duper important. It simply says that if you have a polynomial of degree n, you're going to get n linear factors, okay? And these are our linear factors, okay? There they go. And there will be n of them for degree n. It's as simple as that. And a1, a2, and right up to an can be complex numbers, or real numbers, because reals are subsets of complex, as we know. And k is a constant. Okay, that is the fundamental theorem of algebra, which I'm going to harp on as we go through this exercise because I want you to really get it. The second superstar is the conjugate root theorem. Now, the conjugate root theorem says that if p of z is a polynomial with real, and I emphasize real, all of them have to be real coefficients, then if you find one of the solutions of this equation p of z equals 0, this is it, a plus bi, where a and b are reals, then you know automatically, ladies and gentlemen, that the complex conjugate of that, a minus bi, is also a solution. In other words, if the coefficients are all real, you're either going to get reals or complex conjugate pairs for your solutions. And these are the superstars of complex numbers. Now we're going to factorise some cubics using the remainder theorem or the factor theorem, which you have learned in maths methods, and we're going to apply that theorem to factorise some cubics. So let's have a look at this. Example 1, we've got to factorise this little beastie here, okay? There it is. I'm calling it PZ, okay? P of Z. Now, it's time to guess and check, because I've had a little look at this and I know that I can't group these things 2 by 2, and I know that there's no common factor. I always check that first, okay, because it makes life a lot easier if you do that. I've struck out on both counts, so now I'm going to guess and check. I'm substituting z equals 1 into this expression, and I'm going to see what I get. It's okay, 1 cubed plus 1 squared minus 1 minus 10. Well, I get minus 9, which is not equal to 0, and therefore I know that z minus 1 is not a factor. I'm looking for a factor, okay? Let's try now. Z is minus 1. In the expression, I get minus 1 plus 1. That's minus 1, which is plus 1 minus 10, and wouldn't you know, I get minus 9 again. Wow, that's a coincidence, but it certainly isn't equal to 0, so we've struck out again. So let's try z equals 2 now. We're substituting 2 for the value of z into here. I get 2 cubed, which is 8, plus 2 squared, which is 4, minus 2 minus 10, which is looking mighty fine, because it comes to 0. So, ladies and gentlemen, I know by the factor theorem that because there's no remainder, I know that therefore z minus 2 is a factor. So we've struck gold. All we've got to do now is find the rest of the linear factors, which I'm going to do with the following technique. I call this my famous alpha technique. Now, if you want to, ladies and gentlemen, you can divide z minus 2 into this polynomial here, and you can just get the remaining quadratic, which you can then go on to reduce to linear factors. But I just don't particularly like long division, so I'm going to do it this way, if you don't mind. But you feel free to do long division if you'd prefer. Now, I've got this. I'm saying that this cubic is equal to my newly found factor times some kind of a quadratic. But I know what the front term is and what the back term is. How do I know that? Well, I know that the two leading terms must multiply together to give the leading term over here, which is z cubed. So this has got to be z squared. Similarly, I know that the two trailing terms, that's this one and this one, must multiply together to give minus 10. So if this is a minus 2, that has to be plus 5. So the only one I don't know is this term here, which I've called plus alpha z, and I'm going to work out what the value of alpha is by a nifty little technique which I call the alpha technique. Now, this is what you do. To find the value of alpha, you expand the right-hand side of either the z or the z squared terms of the right-hand side here, and then you equate coefficients with the left-hand side, and it is like magic. So let's expand, for this example, only the z squared terms from the right-hand side. Now, this is what we get. Now, I'll show you how we got that. Each of these terms in the leading bracket multiplied by one of those terms will get you a z squared term. Now, I'll show you. So this z, okay, if we multiply that by the middle term, we'll get alpha z squared, won't we? And if we take this minus 2 in the leading bracket, if we multiply that by the first term of the second bracket, we'll get minus 2z squared. So that's where I got this from, okay? Just expanding the z squared term. If we simplify that a little bit, we'll get minus 2 plus alpha in brackets z squared. Now it's time to do the magic trick. If we equate coefficients with the left-hand side, the z squared term on the left-hand side happens to be this little beastie. It's just plus 1 times z squared, isn't it? So therefore, we know that 1z squared from the left-hand side is equal to minus 2 plus alpha z squared from the right-hand side. Now I'm going to equate my coefficients, and I know that therefore 1 is minus 2 plus alpha, therefore alpha equals 3. Nifty, huh? So therefore, we rewrite pz as z minus 2, which is what we got from our guess and check, if you remember, times this now completed quadratic with the alpha value filled in as 3. All that remains to be done now is to turn this quadratic into two linear factors, and then we've done our work. Now, to do that, all we've got to do is to complete the square. Yep, so let's do that. So we get, for p of z, we get z minus 2 times z squared plus 3z. Let's halve this coefficient to get 3 over 2. Square it, plus 9 over 4, and then minus 9 over 4 straight away again, so we don't alter the value of what's in here, plus 5. Now, these three terms here are my perfect square, which will be z plus 3 over 2 all squared. Then we'll just combine these two terms here, mopping them up to be 4 5s are 20. 20 minus 9 would be 11 over 4, okay, with a plus in front. There she be. This is magnificent, isn't it? Now, what we're going to do now is we're going to turn this little guy into minus 11 over 4i squared, so we get a difference of 2 squares, which you can only do with complex numbers, and we get that equivalent, okay, root 11 over 2 times I all squared. Now we just do the old trick with the difference of 2 squares, and we're going to get that, yeah? How marvellous! Now I've got a little asterisk there, and I'm going to say that I'm checking my two superstar theorems that they work in this instance, which they certainly do, because we've got three linear factors emanating from a cubic, which is what we expected, and because all the coefficients are real, we would expect to have the solutions to be, or the factors to be, I should say, either reals or complex conjugate pairs, which I do. I've got one real, z minus 2, and I've got one complex conjugate pair, which are these two beasties here. So everything checks out. Isn't it great?